Have you ever wondered what makes up everything around us? You know, the trees, the stars, even you and me. The answer lies in a realm so small that it's hidden from our everyday view, the quantum world. In this tiny universe, things behave quite differently from what we experience in our daily lives. Here, particles can be in multiple places at once. It's like having the power to be in Delhi and Mumbai simultaneously. This mysterious and fascinating realm is governed by the laws of quantum mechanics. It's a world where energy, light, and matter exist in discrete units called quanta. Think of it like this. Imagine water not flowing continuously, but rather in tiny droplets. That's quantum. Now, to navigate this subatomic world, we need a special set of tools, quantum numbers. These numbers help us understand the properties and behavior of the tiniest particles in the universe. Imagine you want to send a letter to your friend in Mumbai. You need their complete address, right? You need the house number, street name, city, and state. Similarly, in the quantum world, we use quantum numbers as an address system for electrons within an atom. These numbers are like a unique code that tells us the electron's energy, shape, and orientation in space. Just like each house has a unique address, each electron in an atom has a unique set of quantum numbers. But unlike your friend's address, which can change, the quantum numbers of an electron are fixed, describing its state within the atom. These numbers are essential for understanding how atoms interact with each other and form the molecules that make up our world. Let's delve deeper into the different types of quantum numbers and see how they help us decode the secrets of the atomic world. The first and most basic quantum number is the principal quantum number, denoted by the letter n. This number is fundamental in quantum mechanics and helps us understand the structure of atoms. Think of n as the electron's energy level within the atom. It tells us which shell or orbit the electron is in, much like how we might describe which floor of a building someone is on. Just like floors in a building, electrons occupy different energy levels around the nucleus. These levels are quantized, meaning electrons can only exist in specific energy states, not in between. The ground floor, or the lowest energy level, is assigned n equals 1. This is the closest an electron can be to the nucleus, and it has the least amount of energy. As we go higher, to the first floor, second floor, and so on, the energy level increases, and so does the value of n, 2, 3, 4, and so on. Each step up represents a higher energy state for the electron. The higher the principal quantum number, the farther the electron is from the nucleus and the greater its energy. This means that electrons in higher energy levels are less tightly bound to the nucleus. So, an electron with n equals 3 has more energy than an electron with n equals 2. This difference in energy levels is crucial for understanding how atoms interact with light and other forms of energy. This simple number n gives us vital information about the electron's energy and its average distance from the nucleus. It helps scientists predict the behavior of electrons in different atoms and molecules. It's the first step in understanding the electron's address within the atom. By knowing the principal quantum number, we can start to map out the complex and fascinating world of electron configurations and atomic structure. The principal quantum number also plays a key role in the periodic table of elements. Elements are arranged in such a way that their electron configurations follow a predictable pattern, largely determined by the value of n. For example, in a hydrogen atom, the electron can move between different energy levels by absorbing or emitting energy. This process is governed by the changes in the principal quantum number. When an electron jumps to a higher energy level, it absorbs energy, and when it falls back to a lower level, it releases energy. This release of energy often appears as light, which is why we see spectral lines in atomic spectra. Each element has a unique set of spectral lines, like a fingerprint, which can be used to identify the element and understand its electronic structure. The principal quantum number is a key part of this identification process. Understanding the principal quantum number and its implications helps us grasp the periodic trends in the elements, such as why certain elements have similar chemical properties and why they form specific types of bonds. In summary, the principal quantum number, n, is a fundamental concept in quantum mechanics that provides essential insights into the energy levels and behavior of electrons within atoms. It's a foundational step in the journey to understanding the intricate world of atomic and molecular physics. Section 4. Azimuthal quantum number, L. Unraveling the shape of electron clouds. Now that we know the electron's energy level, let's explore its shape. The shape of an electron's path around the nucleus is not as straightforward as one might think. Electrons don't orbit the nucleus in neat little circles as we often see in simplified diagrams. These classic depictions, like the Bohr model, are useful for basic understanding but don't capture the true complexity of atomic structure. Instead, electrons exist in regions of space called orbitals, which have various shapes. These orbitals are more like clouds where the electron is likely to be found rather than fixed paths. The azimuthal quantum number, denoted by L, determines the shape of these electron clouds. This quantum number is crucial in defining the geometry of the space where an electron is likely to be. L can have values ranging from 0 to n-1. This means that for each principal quantum number n, there are multiple possible shapes for the electron cloud. For example, if n equals 2, then L can be 0 or 1. This gives us two possible shapes for the electron cloud in this energy level. Each value of L corresponds to a specific orbital shape. L equals 0 for a spherical shape known as the s orbital. This is the simplest shape, resembling a sphere. L equals 1 for a dumbbell shape called the p orbital. These orbitals are more complex and look like two lobes extending in opposite directions. L equals 2 for a more complex shape, the d orbital. These orbitals have even more intricate shapes, often resembling clover leaves or other complex forms. And L equals 3 for an even more complex shape, the f orbital. These are the most complex shapes, with multiple lobes and intricate patterns. Imagine blowing soap bubbles. Some bubbles are spherical, while others might be elongated or have more intricate shapes. This variety in shapes is similar to the different orbital shapes determined by the azimuthal quantum number. Similarly, the azimuthal quantum number tells us the shape of the electron cloud, giving us more clues about the electron's address. Understanding these shapes helps scientists predict how atoms will interact with each other, which is fundamental in fields like chemistry and material science. The shapes of these orbitals influence how atoms bond and form molecules. For instance, the way hydrogen and oxygen atoms bond to form water is directly related to the shapes of their electron clouds. Each element on the periodic table has a unique set of orbitals, which explains the diversity of chemical properties and behaviors. The azimuthal quantum number is a key piece of this puzzle, helping us understand the rich tapestry of atomic interactions. As we delve deeper into quantum mechanics, the importance of these quantum numbers becomes even more apparent. They are not just abstract concepts, but practical tools that scientists use to unlock the mysteries of the atomic world. By studying these quantum numbers, researchers can make predictions about electron behavior, energy transitions, and even the properties of new materials. This knowledge is crucial for advancements in technology, medicine, and many other fields. The journey of understanding electron clouds and their shapes is ongoing, with each discovery paving the way for new innovations. From quantum computing to advanced materials, the implications of this knowledge are vast and far-reaching. So, the next time you think about electrons, remember that their clouds are not just random shapes, but are defined by the azimuthal quantum number, each with its own unique and fascinating structure. Section 5. Magnetic quantum number, ML. Navigating the electron's orientation in space. We've determined the electron's energy level and its shape. The energy level tells us how far the electron is from the nucleus, while the shape of the orbital gives us an idea of the region in space where the electron is likely to be found. Now, let's pinpoint its orientation in space. This is crucial because the orientation affects how electrons interact with magnetic fields and other electrons. Imagine holding a magnet near a compass. The compass needle, which is itself a tiny magnet, will align itself with the magnetic field created by the larger magnet. The compass needle will align itself with the magnetic field. This alignment is a direct result of the magnetic forces at play. Similarly, electrons behave like tiny magnets, and their orientation in space is influenced by an external magnetic field. This is because electrons have a property called spin, which gives them a magnetic moment. The magnetic quantum number, denoted by ml, describes the spatial orientation of an electron's orbital. This number is essential for understanding how electrons are arranged in atoms and how they interact with magnetic fields. It can take on integer values ranging from -L to +L, including 0. These values represent the different possible orientations of the electron's orbital in space. For example, if L equals 1, which is a p orbital, then ml can be -1, 0, or +1. Each of these values corresponds to a different orientation of the p orbital. This means there are 3 possible orientations for a p orbital, each pointing in a different direction along the x, y, or z axis. These orientations are crucial for understanding the electron's behavior in different chemical environments. So, the magnetic quantum number adds another layer of detail to our electron address system, specifying the direction of the electron's magnetic moment in space. This helps us predict how electrons will interact with magnetic fields and with each other, which is fundamental for understanding chemical bonding and reactions. By knowing the magnetic quantum number, we can better understand the electron configuration of atoms. This knowledge is essential for predicting the chemical properties of elements and how they will react with one another. The magnetic quantum number also plays a role in electron transitions between different energy levels. When an electron moves from one orbital to another, its orientation in space can change, affecting the energy and properties of the atom. Understanding the magnetic quantum number is not just theoretical. It has practical applications in fields like chemistry, physics, and material science. For instance, it helps in designing better magnetic materials and understanding the behavior of electrons in different environments. Different elements have different magnetic properties based on their electron configurations. The magnetic quantum number helps us understand these properties and predict how elements will behave in magnetic fields. In summary, the magnetic quantum number is a vital part of the quantum mechanical model of the atom. It provides detailed information about the orientation of an electron's orbital, which is essential for understanding the behavior of electrons in atoms and molecules. By mastering the concept of the magnetic quantum number, we gain deeper insights into the fundamental nature of matter and the intricate dance of electrons that underpins the world around us.